Okay, here's a help on polar equation area problem, and it comes with lots of little nuances that go with that type of area problem. So here's two relatively innocuous looking polar equations. They both make circles. You either know that because you recognize the type, or you graphed it. Either way, the hard part about these is knowing what region to graph, because what happens is polar equations are graphed in a particular order, and this one, for instance, that blue circle starts at 0, radical 3, 0, over there on the x-axis, and then it traces out in that direction. So you have to have a sense of, if I want to get a particular region of area, you actually have to put them in the right order, what values come in what order on your integral, lower bound and upper bound. So now that I've got that kind of situation in order, have a sense of where they start and where they end, then I can actually start saying, okay, I'm going to put two areas together. In this case, I'm going to add two areas that I'm going to show you shaded here in a minute, rather than subtract two areas to find the area between things, which we do sometimes as well. But this one's, you have to add two regions together to get that shaded region. That purple region that you see shaded in the yellow region, I'll show you where they come from. But first I have to find out where these circles meet. I happen to know that they do meet at 0, 0. But that thing is that it doesn't happen mutually at the same time. And so there's always some intricacies that go with it. But first let's set them equal, and then let's talk about one of those intersections. The sine of theta over cosine of theta, as I'm solving here by setting those equal and divide by cosine. I see tangent in there, of course. I think, all right, when's tangent of theta equal to radical 3? And one of those times is when theta equals pi over 3, pi over 3. And so we have pi over 3, which would be that, upper, kind of makes sense. It looks like it goes through where those two intersect up there in the first quadrant. So there it is, pi over 3. That's helpful. That gives me some bounded regions I can work with. So as I put this in here, I'm going to get this all set up. Are you ready for this? So now, for the idea of area of polar equations, it's all about little slices of pies you're adding together, sectors we call them. So you do infinite sectors. So the setup for the area is always 1/2 r squared theta, where r is your polar equation, which is thankfully called r. Theta is the measure of the angle, or where it's taking place. I'm sure that's all apparent. If I can't remember where that formula comes from, 1/2 r squared theta, I think, well, put 2 pi into that equation, and I do get pi r squared, the known circle area formula. And then it kind of helps me work backwards into thinking, oh yeah, that's just a proportional chunk of the area of that circle. That's where that formula comes from. Anyhow, here we go. So if I do my red circle, there's the radius would be sine of theta, and then I square it, integrate it, take it times 1/2, and the region on the red circle that I'm going to do is that purple region, and that was from 0 to pi over 3 that got carved out, because the red circle gets started at 0, 0, and then it carves itself out, makes its way up to pi over 3, and it'll be that purple chunk that you see shaded there. Then, so that's sum of infinite sectors from 0 to pi over 3 is what that indicates. Then there's the yellow region, which is that radical 3 cosine theta radius chunk. We square it, integrate it from, now this is pi over 3 to pi over 2 that is traced out on the blue circle, so it's a different timing. And that's shaded in yellow. And that's it. Those are the setup area of infinite sectors from pi over 3 to pi over 2. Now what I've got is everything I need for a calculator to figure out the area, and I can actually plug that in depending on what device you're using. All the known graphing calculators out there can take care of this, and we can get an answer, 0.224186. I think I said that back, 2.221486, or whatever I had said. So now, turning it over, though, we can't live with just doing it with the calculator, though it is the chosen way. I do that any day of the week if I'm just trying to get a result. We do need to have a sense of where that comes from when we're working it by hand. And so one of the things you have to employ is we've got to drop the degree off in that integral. We can't, sine squared is just not so fun to integrate, but if you rewrite it into one of its equivalent forms, like 1/2, we use some double angle formulas mixed with the cosine squared, the plus sine squared equals 1, that triangular formula, you can get these two, which you want to know well whenever you're dealing with polar equations. So these identities are handy because it drops the degree down to a manageable level. And that's what I'm going to do. Sine squared is 1/2 of 1 minus cosine 2 theta, and cosine squared just has a plus because it's in terms of itself. So we'll plop those in their respective places. The squared just disappears, which is great. I can factor out like that 1/2, which we'll do. The radical 3 squared, I'll pull that out front, make it a 3. So it'll be 3/2 out in front of that integral. I might as well do that now. And then I'll pull out the half later as well. But there you go. That's your setup for making that a much more manageable integral. And then I can start doing some antiderivatives, take care of those. The 1/2 sine of integral of 1, of course, is going to be theta. The integral of cosine of 2 theta is sine of 2 theta, but times 1/2 to compensate for, when you take the antiderivative, or the derivative of sine of 2 theta, you get 2 sine cosine theta. Well, this 1/2 there is to compensate for the 2 that is not there in cosine of 2 theta. So there's our antiderivative there. Keep rolling. Now we got 3/4 out front. Theta for the integral of 1. Cosine of 2 theta. The integral antiderivative is 1/2 sine of 2 theta. We'll put in our values, upper and lower. 0, and the first one, when you put in 0, you get out 0 in both cases. Sine of 0 is 0, so we can actually ignore that in the first one. And the right-hand side, if you put pi over 2 in, everything is great, but sine of 2 times pi over 2 is sine of pi, which is 0. So that's where that 0 comes from, you're seeing there. And 1/2 sine of 2 theta is 2 times pi over 3, and the sine of 2 pi over 3 is radical 3 over 2, which you saw in both of these problems. So are both sides of the sum. There you are. Those are the values. We just got some simplification to do, and we're on the home stretch now. So here comes pi over, looking good. I got some things I can add, those pi's, those various pi's. I'll get a common denominator, and we'll make those pi over 6 if we put them together with a denominator of 6. Haven't distributed that 3/4 yet, but I will now, and get a common denominator for all my pi values. And in case you're wondering, that's the rest of this is just take a peek in there, just simplify a little. And we get 5 pi over 24, which came from the pi over 24 is 3/4 times pi over 6, and that 2 pi over 2 times 12, or 24, we can put those together. And then I put my radical 16s together after I distribute the 3/4. And if you noticed a little bit while back, I simplified that. I had 4 radical 3 over 16. And then I just simplified those, cut that down, and made a radical 3 over 4. Same result as I had before with the calculator, but this one's all done up and pretty. So hope that helps. This one's, it's got some stuff to it. These do take a while sometimes, especially by hand. If it's just your calculator, it's no problem once you get the setup, but it is difficult to find that region and how to set up what areas to either merge together to get bounded areas or what areas to subtract. Good luck.